Hello. Hello. Okay. Okay, hello. Okay, we've got 3 people. Okay, hello, you guys. More people. Okay, 4 people. Okay, hello. Can you guys hear me?
Hi, Professor. Yeah, we can hear you.
Hi. Okay. Hi. Good. That's a very friendly response. Thank you. I appreciate it. I like the hi before the. Okay. Here's a great. So while we're getting set up here, and by the way, let me just say again to all of you or any of you, like,
No.
I mean, I know I've mentioned this before. Oh, wait, okay, another person. Okay, no, this is a full house. All right, we got 5. Okay, people are coming. Hold on a sec. I mean, I'm going to say this again, even though it's such a negative thing to say. I mean, you know, I've been doing this for a long time. I really love physics. I love this class. It's one of my favorite classes to teach usually. And usually, even when in real life, even when I don't look forward to it, from the moment I walk into the room for this class, it makes like the time flies and I'm happy and all that. But with this Zoom thing and everything, I'm sure you guys are feeling like I do. When this class is approaching, and I know it's going to be 2.5 hours sitting in front doing Zoom, I mean, it's a dreadful prospect for me. And I can't imagine how dreadful it is for you guys. I mean, because at least I get to talk about what I want to talk about, but I don't know how. I'm thanking you in advance. Every time you even open your Zoom for a 2.5 hour academic ride, I think it's very courageous because, and I'm assuming people are walking in and out while you're doing it. I don't know how any of you get through it, is what I'm saying. So we're trying to make it as livable as possible, but still looking at the more people, but more people are coming, so that's cool. I'm getting the board together ready here. Okay.
Oh my God.
Okay. Okay. And not to say that I'm not looking forward to what we're going to do today, but just it's just this whole world of Zoom is. I will be the only thing that's more scary to me than teaching and learning this way all the time is the prospect of getting used to it. Like I keep trying to get used to it, and I don't know if I really want to get. But all right, here we go. Okay. One question I have to ask, and I have to ask officially. I do want an official response. I'm about to ask something in the chat. Oh, thank you for the yes. Before we get rolling with the word, I'm going to ask something in the chat, and I want people to answer. Honestly, this is super important, especially because of the timing. Very official, important question that I just put in chat. Deeply crucial, important question. I guess if your answer is no, you don't have to answer it. But if anybody's answer to that question is yes, please answer. All right, I'm gonna start this. All right. So I think the answer is no. I mean, if you do play Animal Crossing, you know, the update just, okay, maybe more people coming, cool. So let me actually start by asking this. So we've got a bunch of people, so a bunch of us are here. This is good, a good start. And I know you can hear me. So I want to try to make this as unlectury as possible. I always say that, and then I always fail. But so let me just try to start with a little bit of discussion topic, a point here. You guys had lab yesterday. Oh no, you did not. Wait a minute. Well, that's right. You did not have this is your first time having 102 this week. Is that correct? Because yesterday was a Monday schedule and Monday was a non-schedule. So could someone confirm or deny? You did not? Yes. Okay. Thank you. Okay. Great. So, and the motion, so the last time you had Walters, like last week, the last thing you did with him was motion 3, right? Which was that, I mean, is this, I guess, confirm or deny this?
Yeah, we finished up with motion 2 and 3.
Okay, great, thanks. That's what, which is the stuff we were to, okay, good. That means, well, the good news of that is it means we're all in the same place. That we haven't lost ground. I'm not behind him or something like that. So that's cool. We can press on with, so tell me if this is right. And do I have it right? Because every year we say these, we say them slightly differently. This is my understanding and my recollection is this is your motion 3 here that I've written down at the bottom of the board today. Is that correct? Or
Yes.
Yes. Okay, great. Okay. And I know I talked a lot last week. This week I want to do more. I want you to work on solving problems and stuff that like are taken from our past exams and so forth. So we're gonna have more time to actually work on these things, but they're based on everything I was saying last week. And here's so just to remind you, so I'm now, and I hope, oh, can anybody confirm or deny this too, by the way? Can someone just confirm whether you received? I just want to make sure I'm doing it right because I think there was an issue at the beginning. So even if you didn't read the notes or even if you didn't watch the video or anything, can anybody confirm that you got the notes from me, PDF of the board notes from last Wednesday after we were done? Like, did you get that in your Google Stream?
Yes.
Yes. Okay. And similarly, if you wanted to access it, can anybody confirm whether the recording of that lecture was findable on YouTube? Like, again, I'm not saying if you were there in the lecture, you don't have to watch it again, but can anybody confirm whether in fact it was there or they could find it or if they were notified or anything? Because I don't know if these are, that's a trickier one maybe. And so can I even ask this? I'll say this because we're gonna have a class today and stuff like that, but if there's, I want to make sure, I think these recordings are like, they're awkward and weird and definitely they're completely unnecessary for anybody who doesn't want them. Like if you go to class, there's no reason to be required to watch a lecture again or something. But I think they can be absolutely vital, these recordings, for any period of time that you're not in the class or something on the exam. So I want to make sure at least that you know where to find them if and when you need them. So can anybody confirm or deny that there are any Physics 102 Yaverbaum lectures the fall? Like, would you know where to find them? Or should I give you the link again? And if does somebody want to test while we're doing class, if you want to test it, well, yeah, in fact, let me say, if you want to test this link, please do. But I would like to make sure that you have access to these things if and when you need them, especially when we get to an exam. So has anybody tried the link? Does anybody know where the YouTube stuff is or no? Or can pass it on or no? I just put in the chat, if so, like, I'm not saying I don't know it. I mean, I do, but basically throughout this class, if someone could just confirm that they can find where these 102 lectures is, like, I think there's a playlist, but I don't think I've ever given you an individual link for that individual playlist. And sometimes I'm not sure if I do that right. So I guess I'd like to find from someone in the class, if you tell me if you can find the 102 lectures on YouTube, in case you need it for that. And so if you could even either put that link in the chat at some point in this class, like when you're bored or whatever, or if anybody just has a confidence say, no, I'm checking, like I'm poking around YouTube, I don't see anything, I don't even know what you're talking about, Yaverbaum, then my point won't be, oh, like, why didn't you tell me this before? I'll be like, thanks. And I will, so someone either tell me the link or put in the answer, it's unfindable in the chat, please, like at any point in this class. But in, But in the meantime, we're going to solve problems here today. I want to summarize. So I'm also saying all this because I want to make, since we meet infrequently, I want to make sure things are as clear as possible without being as boring as possible. So like the summary, the quick summary of where we landed last week, which again is, in the notes and in the recording, if you want to check, the summary is, actually, I'm going to leave this for, there's one more word to the sentence. So what I'm writing on the board here, maybe my handwriting is illegible. I'm saying just to summarize where we landed last week, to summarize in English, and then we have to use the mathematical implications of this to solve some problems. But in English, we've been looking at oscillation in the labs in the class, and what we're trying to conclude from last week is that there's a certain kind of oscillation, a certain kind of really regular, really reliable, really patterned or steady oscillation that is called harmonic oscillation in physics. And what's so steady about harmonic oscillation, the precise defining feature of a harmonic oscillator is an oscillator which oscillates at a frequency, okay, which is number one, constant, like a constant frequency, tick tock, tick tock, tick tock, not tick tock, tick, 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 tock, like not that, but more. So a harmonic oscillator is one that's oscillating at a regular frequency, but even more specifically than that, more excitingly, more surprisingly, more powerfully than that, a harmonic oscillator is one whose steady frequency is some number determined by something, but determined independently of, and then that was one key word missing, and I guess I want to ask it, but can anybody fill in the missing word? Like, what's the word that completes this? I feel so obnoxious, but just to keep us together, there's one word missing in this sentence, and this is a takeaway sentence from last week. Like, this is the definition of harmonic. Harmonic oscillation is oscillation for which the frequency is independent of what? Of blank. If anybody could give a shot at this, either in the chat or in their voice, I would be thrilled. And if you're wrong, I still will be so impressed that you said anything. Believe me, I'll be so grateful that you said anything. I won't even remember what the right answer is. If anybody wants to try, could you raise your hand if you hear the question? So like, you don't have to answer the question, but please electronically raise your hand if you understand that I'm asking the group a question right now. I won't punish you for raising your hand, but please, anybody who hears my voice right now, electronically raise your hand, please. If you hear me, please electronically. Oh, maybe I'm not. Maybe there is a problem. Wait a second. Oh, yes. Okay, I see clap. That's funny. I see the applause thing. Thank you.
Sorry, I didn't know where's the hand raised.
Okay, fair enough. No. And thank you. Now I hear your voice. Now you don't know what it's like. Cool, no problem. And now I saw a thumbs up. Thank you, Carolina. And can I repeat?
Carolina.
Okay, and thank you, Ariel, for your honest question. Yes, I can repeat. Well, the one thing I'm saying right now to everybody is, please just, if you hear me at all right now and you're there paying attention, could you please electronically raise your hand or electronically give some electronic indication of aliveness if you hear me at all right now. It's sort of like 1/3 of you. Okay, see, this is what makes this tough. Wait, one person, so one of you here, because what I'm trying to ask is the whole group a question. The question is, and oh my God, and look back in your notes from last time if you want, and of course I'll provide the answer in a second, and then I'm going to stop pulling teeth. And thank you for Suleiman, thank you for raising your hand. Okay, that's cool. I think the takeaway of last week was the definition of harmonic oscillation. That is to say, we're studying oscillation in this class, but we're actually going to study a very specific kind, a kind that is very, very reliable in a very specific, surprising way. We call that way harmonic. And what I'm saying to everybody now is harmonic oscillation is oscillation for which frequency, I'll even add this word also here. For which constant frequency, like, is independent of something. Now, again, constant frequency. Wait. Sorry. I'm sorry. I'm looking at the chat. Interesting. Okay, so wait, I'm just looking at what some. Thank you, Vicky, for what you put in the chat. No matter what, that was definitely helpful that you put the news.
I found your YouTube page, but it only has 2 videos up, and it's from like a couple of months ago.
Wait, my YouTube page only had. Oh, I see what the problem is. That's not. That's a. Oh, okay, thank you. That is very helpful. That you're telling me that. I see why there's confusion, because that's an old YouTube page I didn't even know existed anymore. I don't think, or is.
Hello?
Wait, oh, yes. Hello.
Hi, hello. Thank you.
Oh, wait.
Thank you. Did you?
Wait, now I'm playing the YouTube myself. Okay, this is getting confusing. Hold on a second. Vicky, thank you for saying that. Yes, I see what the problem is. Let me give you, I'll give you all a better link. I think that's a different channel. I mean, I'll say this because I'm going to confuse myself, but I think if you type Professor Yaverbaum, if you type Prof Yaverbaum into the YouTube search field, then you get a channel, which I think is not that one. And it has the picture of John Jay and everything on it. But all right, I'll try to fix this for everybody in a second, but while you're in the breakout rooms. But the word missing in this sentence that I just want to say is the word amplitude. What I just want to really emphasize in English, and I mean, I'll say that, like, I know everybody's like tuning in and out and stuff, but just I want to say this so many times that no matter when you ever tune in, you all hear it. The thing about harmonic oscillation, the thing about these formulas, these equations, these motions, these things that you're getting in lab that seem all kind of maybe mysterious or clunky or disassociated right now, what each of them is trying to say is something about the period or the frequency, the rate of some oscillator. And the thing is, like this motion right here, like it has a lot of symbols in it and everything. It has a lot of things going on. But at the risk of being too repetitive from last week, I'm saying like T is a sorry. Oh, let me look at the chat. Oh, okay. That's really helpful. Thank you again. Thank you. Great. Okay. Thank you, Vicky, and thank you, Tiffany. This is helpful. Again, I'm sorry to keep going back and forth too, but just, and I'll try to put a formal thing. I'll try to put it, something in the Google Classroom so that everybody sees it. But they're saying, well, you guys can read the chat too, obviously, but it is helpful. And again, like, it's good to know what's findable and what happens when we, but yeah, I'll try to make a specific link for the specific playlist that is just, I think there is a playlist for just this class, and maybe one of you two, either Vicky or Tiffany or others, can confirm. I think once you find the correct Professor Yaverbaum channel, I think there is a playlist for just this class. And and of course, whenever I update to it, it notifies anybody who's subscribed or however that works. But so it just, as we get closer to an exam or something, it might be useful to know this. Okay, and it's useful for me to know what's coming across and what's not, because I'm, you never can tell when you do a search on your side. But all right, back to what I'm saying here. this equation, this third motion, it's all constants in a way. It's a relationship of constants, but they're different type of constants. The big point that I was trying to make last time is that L and G are constants. They're numbers that don't change because they describe the materials and the ingredients of the setup of your system, of your oscillator. Like the length of the string, if it's a pendulum, which is what this is talking about, right? This is talking about a pendulum oscillator. L is the length of the string. That's like an ingredient in the system. G is the free fall acceleration due to gravity. Okay, that's an ingredient in our larger system. But T on the left side, that what we find when we take the square root, blah, blah, of L and G, the T is a constant measurement. That's a measurement of like the performance or the output of the system. That's not an input or an ingredient. That's not how you set up the system. That's how well it works, like how much time it takes the pendulum to swing across and back is what T stands for. What this equation is saying is it's an example of the essence of harmonics, which is that the performance of the system is determined entirely by the ingredients. The performance of the system is determined entirely by the ingredients, meaning each tick of this tick-tocker, like each swing, the amount of time it takes to do a swing is entirely determined by how the system is made, as opposed to what? As opposed to how you set up the system, as opposed to the initial conditions or configuration of the system. Specifically, I mean, as opposed to how far back you start the string off. Like what we're really saying here is it does matter how long the string is, but it doesn't matter how long your initial angle is. And that's actually really surprising. Again, I don't want to like overdo the point, but I can't really overdo the point because it is such a big one. We are saying if this is true about a pendulum, this statement, and it is true, very, very, nothing is perfectly true about anything, but it's very, very true. And it gets more and more true the smaller the pendulum angles are and the longer the string is. We're saying here that if you start a pendulum over here at 15 degrees and let it go through like small arcs like that back and forth, or you start off at much more like 35 degrees, like start off at 10 degrees or start off at 20 degrees, much more, and ask it to undergo much longer swings back and forth. We're saying that these little short swings, tick tock, will take the same amount of time as these long swings, tick tock, even though these swings, the thing has to go all the way there and all the way back. This equation is saying it doesn't matter. Like that doesn't figure into the right side of the equation. It doesn't matter where you hold the thing back, whether it's 20 degrees, 10 degrees, whether you're asking this thing to sweep a big arc or a small arc. Either way, all arcs will take the same amount of time. That's what this equation is saying. It's saying bigger, and this is where we had the last, like we're saying bigger swings are necessarily faster swings on average. Like we are saying, if you hold something back, if it's a true harmonic oscillator and truly obeys this equation, then if you hold the bob way back here at 20 degrees and let it go, it starts with a lot of potential energy because you started it back at 20 degrees, like high above the ground, the bottom point. It starts with a lot of potential energy. And therefore, as it's losing its potential energy and converting it to kinetic energy, it will have a lot of kinetic energy at the bottom and on average for the swing. So it'll on average go really fast. Whereas if you bring, but it'll have a long way to go, but it'll go really fast. Whereas a small angle pendulum has a short way to go. So you'd think it would get there in less time, but it moves on average really slow because it starts with less potential energy and therefore has on average less kinetic energy. That's what we're saying. And even that, I get really excited when I think about this for real. Even that argument, even I can follow. Like I wouldn't have thought of it initially. It's not obvious to me, but once I think about it, oh yeah, okay, right. Longer swings I would have thought would take more time. I would have thought longer swings would take more time, but I could see how they don't because I could see how a longer swing on average could entail faster motion, higher speeds. So I could see how something could go faster for that longer trip since it started from a higher up, but still, why would that mean it would work out perfectly? Like, what if it's getting so much more speed that, how do I know that bigger swings aren't actually less time. Apparently the speed compensation works out perfectly. We're arguing, we're actually proving in a way that if it's a true harmonic oscillator, it doesn't matter the size of the oscillation, no matter what, the time of the oscillation will be the same. We're saying time is independent of space. That's what I mean, in effect, when I say period or frequency is independent of amplitude. I mean the tick-tock rate is independent of initial condition. So for like the last time, just to say in English again, that's this. So this is all the significance of any of those equations. The equation, like the equation, this one, the English significance of it is what I'm saying. Any bottom line. So any harmonic oscillator is an oscillator that keeps time independent of space. And that's why a harmonic oscillator is a clock, or any clock is a harmonic oscillator. A harmonic oscillator is the pure essence of what we ever mean by a clock. Any device that keeps time in any way, whether it's a swinging pendulum or a spring-driven pocket watch or an electronic circuit that then makes a digital clock, anything that keeps time is at base some kind of naturally occurring harmonic oscillator. Two examples of which we so far have in class, like the spring and the pendulum. But the harmonic oscillator is whatever you understand about tick-tock, about keeping time, whatever you understand about time keeping itself, that's what the harmonic oscillator does. As what I mean is, as opposed to seconds or minutes or hours or days, like any of those numbers that have to do with time, well, that's just numbers that we impose on time, right? Like there's nothing magic about the second. There's nothing magic about 60 of them collected together. And we could have made up the unit, like, you know, we could have made up the Yaver minute and it could have consisted of 200 seconds or something like that. All of those are just arbitrary, just not arbitrary, but they're all just decisions. But the idea of keeping regular time, which is what a clock has to do, whatever time you set it to and whatever intervals you divide it into, keeping regular time means being a harmonic oscillator. That in English. Now, yeah, because we want to do some problems based on. Well, are any questions or any comments at all? So I don't know how there could be, but okay. Now we have to apply this now to radians and all that. I'm flipping back in the notes now in front of all of you to see. Right. So we did this. Yes. Okay. So let's do a quick example now to warm up, or to get back to the math of what we were doing last time. Pardon me. Okay, please do this now. This thing that's on the board, this is an exercise. I think I'm going to put you in. It's not meant to be hard or crazy or anything. It's in, nor is it meant to be insulting or boring. It's just an exercise in what we were saying last time. So I'm saying, imagine some pendulum. We release it from some small angle. Some small initial angle, theta naught. It's got a mass of m. The pendulum length is L. And the first fact I'm telling you is that this pendulum is reliable and regular. Like, we pull it back to this angle, we let it go, it swings back and forth, and we find regularly it takes about 20 seconds to complete a round trip, right? What that probably realistically means is we let it go for a long time. We start our stopwatch, just like you did in lab 1 in principle. We start our stopwatch at some point when the mass is over here. We let it go back and forth like 20 times. We look at our stopwatch at the end of 20 times and we divide by 20 or I mean 100 times or whatever, but we divide by that number and we find in the lab that this pendulum regularly requires 20 seconds to make a round trip. In other words, its period is 20 seconds. So I'm going to ask you a couple of questions about it. And by the way, and you can't, this sheet won't translate into the breakout rooms, right? I mean, my board won't just automatically go. And so please do copy this down or whatever before I put you in breakout rooms. This is the setup. The one fact, so far, I'm not telling you how massive the pendulum is, and I'm not telling you how long the length of the string is. We can assume this is on Earth, but I am telling you that the pendulum takes 20 seconds to go back and forth. So my first question about that is, okay, what's its standard frequency measured in hertz? This goes back, you'd have to look in your notes from last week or something, but from its period, but it's not supposed to be a trick, just like do it. So I want its standard frequency in hertz. Then from that, I want you to figure out or tell me what is its Oh, I didn't finish writing. What is its angular frequency? That's not measured in hertz. That's measured in radians per second. And I lost the word here. Sorry. Find its angular frequency. Now I'm going to have to turn the page here in a moment. So I'm going to pause for a second so you can copy this down because there's a couple more questions I'm going to ask about it. And then well, I think I can put it here. And the final question is, okay, so the third question I want to know is how long is the string? Now, the truth is you could answer these questions sort of in any order. I'm not actually guaranteeing that you can answer them in any order. You don't need to do number one first, and it's not necessarily for some deep reason that I ask number one first. But I'd like to get these three answers. And I want to ask one last one. This will either be the hardest or not, but one last one. But if you can get all three and not this, that's perfectly fair and impressive and not surprising. Actually, no, I'm not even going to do it because it's going to get too crowded and it's going to confuse everybody. There's one fourth question to ask here, but I'll either put them in the breakout rooms or ask when you come back. I want to work on these first. I'm going to put you in breakout rooms to do these three. Could I just get a show of hands that it's clear what we're about to do? Like you may not have answers yet, you may not know what to do or how, but can I get some confirmation that you hear me, that you understand that you're about to work on this problem in breakout rooms? Okay, could you raise your hand electronically if you hear me right now? Thank you. Okay, that's good. Thank you. That's enough. Okay, that's four. Thank you. All right, that's awesome. So okay, cool. Can everybody hear? So four people are with me. So we're about to go into breakout rooms. And I know that can be sort of miserable. Again, let me just say, I don't remember if we've done them a lot. I know breakout rooms are kind of miserable sometimes, but they're also kind of super productive sometimes. When I put you in the rooms, please, if someone's not showing up in your room or something, send me a message. It's not, or something, but like the main point of the room is so that you have time to quietly think and or talk without worrying about what I think. That's the main purpose. I'm not putting you there to force you to work or so that I can sneak up on you and check that you're working. I'm putting you there so that you could actually admit to yourself where you are in this material and like not have to worry that I would think something critical or something. So please, when I open these breakout rooms, please go to them. And if someone in the room wants to just quietly work and not talk much, just that's cool. Let that person do that. But whoever that person is, if you, whoever you are, just want to quietly work and not deal with other people, just still at least electronically let them know you're there. Be like, yeah, I'm here, I'm totally here, but I just need to think. I'm like, ignore me, I'm thinking. And you can do that. But just, I want these, it's supposed to be a safe place is the idea. But so you're going to work on this problem right here on the board. You do have to copy it before you bring it in. It may be a joke. For some of you, you might do this in 2 seconds. Some of you might have already solved this problem while I'm talking. If that is the case, then please, in the room, your job is to sell that understanding to everybody else in the room. It will benefit you even more than them if you can try to get everybody else in your room to see what you see. If you see how to do this. If you don't, please work together, and then we'll come back. But this is the question for, and then Ms. Lee, I totally appreciate that you're raising your hand. Thank you. Oh, okay. You could put it down now if you want, or unless you have a question, in which case please ask it. Or Ms. Lee, do you have a question? Or okay. Is it Nayun? Do I say Nayun? Oops. Am I saying it right? Or
Yes.
okay, thanks. Okay, I'm not trying to, and you can put, I'm not trying to single anybody else out. I'm just, okay, cool. All right, so we're gonna go to breakout rooms and we're gonna do this problem. So when you get your assignment, please, so just go straight to your room, please, and work on it. Great, thank you, thank you, thank you. Okay, great, thank you, great, thank you. Hi, sorry to interrupt. Sorry, hello? Hello, can you? Hi, sorry. Well, I am interrupting, but only to ask if that is, are you guys okay? Are you like, do you need more time? Or are you done? Are you in the middle of a discussion? Do you have questions? What?
Professor, I just want to make sure. So for question 1, we're looking for frequency.
Yes. Yes.
And question 2, we're looking for angular frequency.
Yes.
And
Yes.
the last question is string length.
Yes, totally.
Okay. Thank you.
No problem. So does that mean you could use more? So if I walked away right now, you would know what you would use the time. Is that right? I mean, you know.
Have you working?
Sorry.
Do that.
I mean, so you're good to go, or you're done, or you're.
No, I don't need it.
Oh, and Professor, last question. We're not giving the mass, correct?
Correct. Correct. You're not. That's right.
Huh?
That's right. Correct. So am I right to think, but you know what to do? And if I walk, I mean, are you good to go then? Or do you want more time, or do you want to stop?
I answered the first 2 questions. I'm having a little trouble with the last one.
Oh, okay, fair enough. Fair. And I'll give you a hint then. And by the way, are you the only, is everybody else in the room, or are you the only?
I've been working independently.
Oh, wow. Okay. Wait, and sorry, you are Vicky or you are Tiffany who's talking right now? Sorry.
Vicky.
Sorry.
Oh, okay. But, so
You got it?
so thank you, Vicky. But then, so Tiffany, you're here too, right? Yeah, okay. But you guys are not particularly working together. Okay, okay. And Nayun, are you, but thank you, wait. Nayun, are you in here also, or?
Yeah, I'm here.
Okay, so, all right, so just to be honest, so so you guys are cool, but not really working together, is that right?
You want to still with potatoes and white rice? That's fine.
Okay, I think I get it. All right, I'm gonna move on to the next room, but all right, I think thank you, guys. Okay. Oh, hello. Sorry to interrupt. Hello, folks. Sorry to interrupt. But I am here to interrupt, kind of, or at least to check it. Can you guys hear me? Anybody? Hello, guys in the room.
Yes, I can hear you.
Okay, thank you. And are you the only one? Is everybody Carol? I mean, thank you, Katerina. Is Carolina or Anastasia or Samantha here also in one way or another?
I can hear you, Professor.
Okay, thanks. Okay. So are you guys good to go? Do you need, I'm gathering from the other rooms, you're working, but you're not really working together. Is that, which is fine, like whatever it takes is fine, but do you want more time, or do you want a hint, or do you want to gather back and hear the answers?
Honestly, I would like to go back and hear the answers.
Fair enough. All right. You know what? That is honest, and that is direct. Okay. And I'm happy to do that, but and if I didn't ask you, do you have any, like, I'm not going to ask you for them, but did you get any answers at all, and you want to know if they're right, or you have no idea what to do, and I'm not putting you on the spot to show me what you did, but I mean, did you guys get anywhere, or just totally stuck?
For me, I'm kind of confused, so that's why I wanted to see the answer.
Okay, I got it. All right, we'll go back. I will go back and okay. But you know what the question is, yes? I mean, you know what you're, all right, well, we'll go back. We'll go back. All right, okay. Got it. Thank you.
he talked to me and Lou at 2:00, and he said he was gonna reach out to the others.
Hello, hello, hello. Oh, thank you for having me. Okay, hello, hello. All right, welcome back. I know this is rough. So I visited a couple of rooms and and I know the rooms can be rough sometimes. All right, I'm gonna go, we're gonna try to find different ways to spice this up or something, because yeah, I know this is, it is what it is, but all right, I'm gonna, I mean, like the more anybody says anything, the better it is for everybody, I think, really. So, and I know, look, the problem with this whole, one of many problems with this whole Zoom thing is when you're saying something, you're really saying something in the class, right? Like to raise your hand in a Zoom class, like all of a sudden your just name is big on the screen, and like everybody knows exactly that it's you talking. And if you say something wrong, then like it seems like it's forever, and then it's in a recording and all that. We'll try every way to get around that. I got to tell everybody, I promise you, in every possible way, anybody who is saying anything or adding anything to this class, that is being worth its weight in gold so much more than what particularly anybody's saying. Like whatever class participation has ever meant, like point value wise, like the people get points for class participation. I so promise you that it really is operating here in this environment, that if you have the guts to talk or somehow make contributions and somehow get me to know your name, you are doing yourself. I'm talking to everybody right now, and I'm complimenting those of you who have said things like at all, and encouraging those of you who haven't. The more you just get me to know you somehow, I could know you as the wrongest physics person in the world. Everything you might say, let's just imagine the worst case scenario, it was like wrong physics from day one. And I would still think of you totally as a strong physics student and one who's going to be beefing up her or his grade by virtue of that, like for real, because it's hard to do this class, and anybody, for all of us, and anybody who says anything is making it easier on everyone, because anybody who says anything, whether it's in the chat or in the rooms or whatever, if you say anything at any time, and even with your video off, blah, 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 you say anything at any time, it helps me know where people are, and it improves the situation by that at least amount. Like, so if anybody at any point says like, you're going too fast, like we don't even know what you're talking about. Or if anybody says, yeah, dude, seriously, we know we've done this 50 times, please. Like, you could be as polite or not as you want, but if you let me know where you are, it helps me. So anyway, that said, I'm going to just like go over this problem now, because in the breakout rooms, it seemed like people were like, ready to hear. But if anybody wants to say anything, like how they started it or where they got stuck, because I will say this too, I understand people get stuck, but this is meant to be a straightforward exercise. Like, if you do understand what the question is, I am kind of asking to plug and chug from the notes from last week. So definitely, if nothing else, please have the notes open from last week. That would help. But I'm going to start it. But if anybody wants to start it off for me, like the given is a period of 20 seconds. It's true. The mass is not given. That's on purpose. The length of the string is not given. The initial angle is not even yet given. All that's given is that the period is 20 seconds. That much we know. And so the first question I'm asking is, what's its frequency in hertz put in English? I'm really asking if it takes 20 seconds for this thing, if it takes 20 seconds to do a round trip. So like 1 Mississippi, 2 Mississippi, 3 Mississippi, 4, 10 Mississippi, 11 Mississippi, 12, 20. Like, that's what I mean by period, the amount of time for one round trip. Then I want to know, how many round trips does it make per second? That's really all I'm asking in question one. I'm asking if its period is 20 seconds per cycle, then at what rate does it cycle through seconds? How many cycles per second does it do, which we call hertz? If it's 20 seconds, oh, is that a Vicky? Is that a yes? Is that a or no? Oh no, sorry.
So for this problem, I used the equation T = 1 over F.
Yes.
So I got 1 over 20 = 0.05 hertz.
Yes, you just made my day. Seriously, like, okay, yes, that's exactly. And I'm not trying to overdo it. I'm not trying to blow smoke up your. Thank you. That was exactly what I'm looking for. That makes me feel alive. And it was exactly well explained. And there she is. Yes, ladies and gentlemen, you don't know what a difference that makes to the world. All right. So yeah, I'm doing exactly what she said. She said, oh, she said, oh, you want standard frequency? Well, that is just always the reciprocal of period. She said, like the equation from last week, exactly. And that means 1 over this 20 seconds per cycle. So yes, absolutely, 1 over 20 is 0.05 cycles per second. And that's a standard frequency. And 1 cycle per second we call a hertz. So the answer to this would be, oh, I'm so overjoyed. I might even end class early now because of that. Okay, so that is the answer. Yes, 0.05 hertz. Oh, wow, look at that. Look at that. That's awesome. Now we're talking. All right, totally see that. And I don't know if can I even get that bigger for everybody? That's good.
I could try to send it as a picture in the chat.
Yeah, if you can, that's great. That would be great. Thank you. Now God, it suddenly feels like education. I mean, I don't know whether you just got your tuition worth or I just got my salary worth, but yes, that would, yeah, if you could put a picture in the chat. But yeah, that's exactly right. And to everybody, like, okay, so that's an equation. Like, what's the big deal of a physics equation? Well, first of all, just again, that Hertz number, Hertz are real things. Like a number a standard frequency of 0.05 Hertz is a very small frequency. 0.05 is small, but it's real. It means you're doing 1/20th of a cycle per second. It's just saying if you do 20 seconds per cycle, then in 1 second, you've only completed a 20th of a cycle. Like we said last time, Hertz numbers that are more realistic that people tend to hear are like radio station numbers, like you hear like NPR is 93.9 megahertz. That literally does mean it's cycling at 93.9 million cycles per second. So these numbers do mean something. But anyway, yes, if she sent that around or when she sends it, that's the answer to that one. But then now the idea is we're going from the stuff that we can measure and count and see. Like I'm trying to say, I could imagine seeing a pendulum taking 20 seconds to do a cycle. Like that's supposed to be something you could imagine. You can even imagine making that measurement. Then the frequency that we just figured out from that, it's a little harder to imagine, but it means the same thing. Like if it's going 20 seconds, then it's only gone 1/20th of the way by the time 1 second has elapsed. That's all we're saying. Well, now we're going to move it one more step mathematical, like one more step abstract and less hard to picture. The next question was, what is the angular and now, is there anybody else who, I mean, it totally could be Vicky. Oh, great. Cool. We're going to chat here. I'm just looking at, I'm so happy, which tells you something, I guess, but that's cool. She totally shared a PDF. I'm clicking it. That's great. All right. In the chat is a better handwriting version of what I was, look at that. Oh, and there, all right. I'm even going to take advantage of it. Okay. I'm totally now. I hope I'm not punishing a good deed, or however they say, no good deed goes unpunished. But I'm looking at what was just put in the chat. Let me just see. Yeah, wait a minute. In fact, hold on. Okay, I think I just, not sure. I might, and I hope I didn't violate privacy or something. Wait. I might have just lost. I'm trying to actually share that screen. What did I? I just lost my screen. Sorry, hold on. Oh yeah. So do people see?
I can see the share screen.
You can. Okay, thank you. Thank you. Okay. So and it's good. First of all, her handwriting is better than mine, so that's helpful. and it's clearly organized. It's exact, and this does make me, I'm very happy. Like in at least one room, and oh, I guess it was hers, but in at least one room, there was some talk about some clarity on question 1 and 2, but they hadn't seen question. Anyway, this shows me where people are too, so it's good. That question 2, absolutely right. Absolutely, from last week. Oh, absolutely right. Oh, cool. Even I never even thought to say it that way. That's cool. Yes, absolutely right. Number. I want to, if I may, I'm going to make one minor qualification or modification. But how do I get back? Hold on a second. Sorry. Just one thing.
Well, you'd be surprised. I think it's both. I think both are true. I think some of them are better than others. And yeah, I think there's room for growth. So feel free to let me know. I was talking to David Kay yesterday, and one thing we were thinking about, it could drive us crazy, but we're just thinking about it, is because Tiffany's work is not like a traditional looking sukkah. It's like a 1930s movie house. That there's no reason that has to go into the storage shed right away after Sukkot, that if the LA Museum only has it up for like 9-10 days, that if there's someplace else that wants it and will absorb the cost of shipping, then, you know.
Okay, so I totally agree with this. And now I'm just writing it in my handwriting. And for anybody, you know, I never get tired of writing these things. Like even if any of those of you who also got the right answer, it doesn't hurt to keep writing these things over in the different kinds of ways and getting used to them. For the second one, I do totally agree with her in like, and there's a number of steps. It always looks easy once you've done it, but it never looks easy until you do it. So a couple of things about what Vicky did. First of all, yeah, angular frequency is the thing that we signify with a lowercase omega. Like this thing is, that symbol is supposed to be a lowercase omega. It is what we use for angular frequency. And absolutely, I didn't even remember if I told you this or if she put it this way, but she's totally right. Angular frequency can be thought of as 2 pi over period. Or it's absolutely equivalently to say it's 2 pi times the standard frequency. Whichever way makes more sense to any of you. Where the 2 pi is coming from, just remember the key to this whole thing is that one cycle equals 2 pi radians. So when we're changing from regular frequency to angular frequency, we're just converting in effect by a factor of 2 pi radians per cycle. And so I totally agree. So you can say 2 pi radian. So if you have a frequency of 0.05, every one of those cycles that you're doing per second is equivalent to 2 pi radians. So you can write it either of these two ways, and then you do 2 pi divided by 20 seconds, just like Vicky did. And you get, just like she said, like 0.031 or something. I now forget what it was. Right. But now here's just the one qualification I want to say. What you end up getting when you get omega, the approximately 0.314, is now this is measured in radians per second. So technically standard frequency is in cycles per second. This one is in radians per second, and they differ only, and the whole connection is, again, we're saying each time you do like, again, the circle that we're picturing, like where 2 pi is coming into play here, or yeah, why we're getting into radians is because we're examining something that is cyclical, and it's easiest to analyze cycles with all the math that we've already invented or already understand for circles. The thing that a cycle and a circle have in common, besides the obvious, they both behave in a way that's independent of size. Like anything I know about circles, like that, anything I know about circles, like that 2 pi is the ratio of the circumference to the radius is true regardless of how big that radius is. Anything that I know about circles never requires me to know how big the circle is. It's true of all circles. And that's the same thing with all cycles. So we're now converting what we can measure in the lab into something that's mathematically useful, radians per second, omega. And that's going to enable us to get more information in a fourth question that I'm going to ask. Although before I ask the fourth question, there was this third question. And this is where I think a lot of the groups maybe stopped. But I totally agree with what's happening so far. The third question was, how long is the string? Now, I may want to, before I say anything more about this, I might want to turn it back to you guys, the class, because one reason this question might be confusing after you get question 1 and 2 is often the next question would be based on 1 and 2. I have to admit, this question I'm asking here is not, you can't get it from having done number 2 just now. You could get this question right away. You could just get this first before you even converted to angular frequency like we just did. Like my big hint about this one is just an application of the motion that started this whole discussion, motion number 3. In order to get the answer to this question, I'm saying to the whole class now, take another moment and look at motion 3. I think you'll find that you have all the information you need in order to answer this question. And so I'm not going to put back in breakout rooms or anything, but I'm just going to take them. And Vicky has definitely done yeoman's work today. I mean, like a ton. So if I can encourage anybody else to throw something in a minute or two of your thoughts, that would diversify things a bit. So I'm asking question 3 is how long is the string? I'm admitting whether you understood 1 and 2 or not, it's not actually based on 1 and 2. It's its own question that could be answered right away if you just look at motion number 3. So I'll give you a second to think about it. But okay, so I sort of want to challenge or ask us if anybody could try to get this in addition to Vicky or besides Vicky, anybody wants to jump up to this one, it would be terrific. I think this one's well, I'll give you a couple more minutes too, but it is a one-stepper. Like there is one equation to use and it is like a plugin, if you understand. But you do have to rearrange the equation, that's for sure.
I don't know. Is it so? Have you had that trouble when you're posting it? Okay. So you've just noticed, and it's on what platform is it?
So any thoughts from anybody about how long? Any thoughts?
No.
Or can we start with this? Can you please raise your hand if you know what the question is?
So Professor, for motion 3, I know, I'm sorry, I'm keep
Do
answering.
it, go.
The equation that I keep looking at is the number 4 and number 5, the t equals a square root of L and a equals 2 pi square root of 1 over G.
Yes. Oh,
I know
okay.
the main equation is the t equals 2 pi square root of L over G, but we don't have G.
Oh, yes. Oh, wait. Okay. That is the one. You are right. And you are rocking again. You're totally right. That's the one to use. But, oh, but either, if you don't have G, that's either my bad or you. Okay. G, you don't. That's
G is
interesting.
gravity, isn't it?
Yes, 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 yes. So maybe you don't explicitly have G. I guess we're assuming you knew it from from the other physics class or something. But yes, yes, by G. Okay, wait, actually, I have another on the next page.
Yeah, me too. And I would say like when we were talking to the fellow who was going to talk to the artist.
Totally fair point, and totally again showing that you're right on top of things. Yeah, I do. Oh, yes, that equation that Vicky just said is the equation I'm having in mind here. Oh, and she mentioned two, and by the way, that's another good point too. She mentioned both of the motions, and they're both useful. One was kind of like what we were using to get the other one, like where the one that actually has the equality sign is the more directly useful one here for sure. She's talking about this, and I'm talking what I think I called motion 3. We're talking about this. And again, this came up last week too. That isn't that, and she said it right. I mean, Vicky said it right just now, but that it's easy to not read it right, that numerator in the square root is supposed to be a lowercase L, not the number 1. It always, no matter who draws it, it always ends up looking like a number 1, but it's supposed to be an L, and that is the equation we're talking about. And yeah, that lowercase g, in theory, this comes from physics 101, but this always throws people off too. That lowercase g, whenever we use it in physics, we mean, oh, she goes, all right, let me see what's going on. Or actually, could you do the photograph thing again, or the image thing? That would be great.
Sure.
Okay, that's totally awesome. And yeah, see, this is just like, it's whether it's, is this class, is it tutor, who knows? But I'll just say while she's putting that in the chat, what was I just saying? Oh, by lowercase g, we always mean in physics the free fall acceleration constant, like whatever it might be. In other words, you could be solving a problem about the moon, and we would use the letter g to refer to the constant rate at which things fall near the moon, which happens to be a different number. G just always means that concept. And it, but on the surface, near the surface of the Earth, where we're doing all this, we do find that number, we can measure that number very, very precisely. We can measure this number very, very precisely, this G number. So I'm on a little bit of a sidebar right now to everybody, just to try to put things in perspective or make things interesting or whatever, or stall. That number G, I want to make clear, you notice I start off with a triple equal sign here up at the top of the page. That means strong equality by definition. Like triple equal sign means G always refers to those words because that's just what we mean by definition. But now as to the number that you're supposed to plug in for G, all of a sudden now I have these squiggly double equal sign, meaning not only is it not true by definition, but now I'm giving you an approximation. Now that can make people uncomfortable in science sometimes when we get approximate. Some people have been doing science to a point where what they like about it is the seeming precision and exactitude, and people can get uncomfortable, especially in physics class, when we start sounding approximate about things. The truth is, what I think is, what's actually good about science is that it's actually much more honest about how precise and how imprecise it is in different contexts. And we can measure gravity, the acceleration due to gravity, super precisely. Make no mistake, like it's a very easy thing to measure to an incredibly high number of significant digits. Like in high-tech labs, if they're still bothering, they could give you the acceleration due to gravity, out to 59 million digits. But here's the thing about that. First of all, the more precisely you're measuring gravity, the more you find that it actually differs slightly from height to height or part of the Earth to part of the Earth. Like actually, if you're that precise about it, then your number is not even going to, if you measure it in Colorado, it's not even quite the same number as we should be using in New York. Or in fact, depending on what apartment building you're in New York right now, in this, we all have slightly different gravity numbers. Second of all, and I'm just trying to, again, just put this in perspective or just be interesting or whatever, but second of all, about this number, I want you to, those numbers, the gravity, the digits, if you recognize this number 9.8, and you even remember from high school or something, someone saying 9.81 or something, it might seem like I'm being sloppy if I just round this number to 10, which I absolutely am going to do. It might seem sloppy or irresponsible or unscientific to change the number 9.81 to change it to 9.8 and then change that to 10. But I'm here to tell you, no, that's actually the attitude of physics is absolutely to do that, because if I'm going to be precise, I mean, if we're in the lab, we'll be more careful, a little bit more careful, but not much, because if I'm in the lab, I know these digits in the number 9.8, they go on forever without repeat or pattern, like pi, like just a little, word from our sponsor here to everybody. That number pi that you've heard of your whole life, that all the digits go on forever without repeat, without pattern, that is a super interesting thing, that like the numbers just keep going on, but it's actually not just only true about pi. It's true about many, 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 many numbers. And in fact, most numbers that we ever find in nature are like that. G is one of them. It goes on forever without repeat. So anywhere you chop digits, I'm just, again, just saying this because it's true. Anywhere you decide to chop off digits with that G number, you're making a decision to chop off digits, and you have to. You have to do it somewhere. No one's ever going to write down the G number precisely perfectly, because we precisely perfectly know it can't be done. So you got to chop off digits somewhere. And once you're chopping off digits, what we do in physics, we chop off digits to make it convenient. Instead of 9.8 all the time, whenever possible, if we're not in the lab, we just call it 10, because it makes all of our multiplication and everything that much easier, and we don't lose any perspective. Do we make it negative or positive? Last point to everybody, this G number, that depends on your coordinate system. Like the number itself is just the number. If you're in a situation where things are going up and down and you have to distinguish between down and up, then down might be called negative and this number might be negative. But that's only if and when it's useful. The number points down, and that's all I'm saying about it. So now, having said that, that was what Vicky, I'm looking in the chat. Hold on a second, sorry. Oh yeah, cool, I almost forgot it. All right, so I'm gonna now open this chat thing, sorry. And I'm gonna get my tuition worth and Vicky's gonna get her salary worth, or something backwards, something like that. How do I, and there it is, oh yeah. And there it is. Right. Nice. Oh, yes, yeah. Okay, so no one can see what I'm, sorry, hold on. But yes, right. Nice. Oh, yes. 4 divided by 6. 400 divided by 400. Oh, yes. I'm just checking. I'm about to put it. I'm just making absolutely sure I totally agree. 400 divided by 50. 400.
I think it's like, it's supposed, and then the museum wants it up an extra week, but there's more security costs.
I think,
Like they're trying to figure out, who can.
Well, yes, no, this is awesome. I'm about to post this. I'm just checking the.
Make a little more happen. And they always played it differently with the budget because Tiffany was already on their team. And so they always plan to use the funds a little bit differently.
Oh, yes. Oh, this is great. Yes, this is perfect. Sorry, I'm being, okay. I'm going to post this. That's really great.
In an okay way. Everybody likes everybody. There's no
Okay. Yes. If everybody could see. So this is perfect. I mean, I'm not to be weird or anything, but like I would welcome anybody to copy this. This is the answer I'm looking for, or the solution I'm looking for. Again, and everybody does things their own way. So really, I'm doing this to engage in a conversation with a person who is engaging in a conversation, but also like, this is what I would write on my board. So please, everybody do write it. And then I'm also just going to show you my way that I would do it, which would be slightly different. Like, because it is a personal exploration. But she's totally right. I'll give you one more second to copy that, and then I'll show you. Sorry, I know it just disappeared. Tell me you want to see it again, anybody, but you could also see it this way. I'm gonna do the same thing that Vicky just did. But I'm just gonna, just a style difference, or just a way, and basically, this, what I'm about to do may be only benefiting her, because it's just a different way to think. Like, the more confident anybody gets with these things, the more I would encourage anybody to postpone the numbers as long as possible. It's what nobody wants to do at first. Everybody wants to plug in the numbers at first because the numbers feel like the most concrete thing we know about a situation. But the more we can get in the habit of saying, so I'm going to do exactly what she just did, but I'm just going to delay on the numbers, like as an exercise of like willpower, in order to see the generalized physics pop out. So in other words, she's saying,
it was the right time. Like, if we had tried to do it around Yom Kippur, it would have gotten washed over. But Sukkot is a different thing.
right, this is the problem, right? I'm just rewriting for the 50th time. But now, and we already know the answer, Vicky got it for us. But I'm saying I could, instead of putting one option one is put it. Option one in general for solving any physics problem is, and I often do it, is what we just saw, is plug in numbers and rearrange accordingly. And when you do that, what you're in effect doing is you're applying the problem to the particular situation, like the particular fact of the numbers, and then you're extracting a general truth from that. Another option that for solving problems, and tell me if you want me to go back to that page. Oh wait, I'm sorry, hold on. If you want me to go back, what is it? Hold on one sec, I'll be with you. Another approach is this. Okay, the second strategy I'm just saying to everybody that I'm showing is instead of moving from plugging in the numbers to rearranging, when you do that, you're in effect moving from particular to general. You're moving from relevant to abstractly true. I'm actually recommending, and this is harder than it sounds, people don't like to do this for the very reason that it is worth doing, which is it's not intuitive. It's not the first instinct, but it's longer term stronger to first always write down things that are true and then make them relevant, rather than trying to write down things that are relevant and then make them true. If you write down things that are true and then relevant, it in effect means you're delaying the possibility of error as long as possible, and you're building up correctness while you delay it. So from an exam perspective, you're accumulating a lot more points if you always start with true and move to relevant, rather than start with relevant and move to true. So what I mean in this case is just this, is saying, okay, what was given was t equals 2 pi this. Instead of plugging in numbers now, I'm going to just rearrange. I'm looking for L. So I'm going to treat it as an algebra problem first, right? Like this is where all the math comes in and stuff. I treat this as an algebra problem before even looking at the lab data. And I say, and I square both sides and say, okay, t squared equals 4 pi squared L over G, right? Because I'm looking for L here. I'm looking for L. So I'm going to just keep, so I'm saying, solving algebraically for L. So I'm just doing, once you know that that's what you're doing, it's never hard algebra. It's just a question of making the decision to actually do it. I'm looking for L, so I'm going to multiply both sides. And then I'm going to divide both sides by 4 pi squared. Now this looks much more complicated, honestly, than what Vicky did. It does. The reason people don't do this, students, I mean, well, people, as you're learning, people don't tend to do this because it looks really intimidating. It looks like each one of these lines might look to you like a whole nother equation that I asked you to memorize, you think, and you didn't, or something, or that you're supposed to memorize and it's too much. But I'm not saying to memorize anything. Each one of these is an equation. That's the thing. Each one of these lines, if this algebra is right, then every one of these steps is an equation that could be useful to someone someday, or could already have been, but I would never bother to memorize because I could always just figure it out like I just did. But each one of these steps is true if the algebra is right, regardless of which pendulum or which particular measurements I'm using. This is now true for all time. Like given a period of 20 seconds, I have a function here where I can plug in right now. I have what I want, which is a rule that tells me how to get L if I plug in T. So now I will use this rule and plug in. Now I'm going to do exactly what Vicky did, but it won't look like it. The numbers will be arranged differently, but oops, sorry. Again, this looks like I'm about to plug into this equation. This looks like a formula that could be on the back of a physics textbook. It totally is, except it would never be. I mean, it is a totally valid equation, but I would never memorize it because it's only useful for exactly this circumstance. And I'm saying we can't get the length of the string exactly. It's approximate because we're using an approximate value for gravity, but we always are using an approximate value for gravity. For that matter, I'm now going to use an approximate value for pi too. Right. And so I think you all should take a moment to there's no, pi doesn't have any units, 4 doesn't have any units. There are units on the top. The second squareds are going to cancel. You'll see, hopefully you see the seconds. Well, right. Right, but notice you really 20. notice we're really squaring 20 seconds. We are not squaring 20 and then putting seconds after it. We're squaring 20 seconds. So when you put this into your calculator, you're going to square the number 20, but we are also squaring the seconds. So they cancel out with the squared seconds under the M, and we're left with just meters, which is great because that's what we're looking for, a length. So you can all do this on your calculator. I'm going to ask, please do it while I join the page, but you should get a number or verify the number that Vicky already got. Or actually, could someone, just so I know I'm alive, I'll actually ask you, and I know Vicky had to leave. Could someone else give me, when you get it, give me what the final answer is? Assume I don't have a. Yes, thank you. Okay. Thank you very much, Samantha. I appreciate it. You, and I'm telling you again, I can't say this enough. Let's say God forbid, and I'm using her name in vain and I apologize, but thank you for, Samantha had the guts and the helpfulness to put something in the public chat. She could have put any number and cool. Okay. She could have put any number and I would be this excited, honestly, just that we're like engaging this way. It happens though that she put exactly the freaking right number. Not, it doesn't happen. She did it right. She plugged in right. Okay. And yeah, maybe this is just a plugin at this point. But you know, we got to do, yes. So I'm going to assume at this point, or I'm inferring that at least with two people in the room know what's going on. I mean, Samantha definitely being one of them. I'm inferring that Samantha knows what's going on, that maybe I could move on and try to make this more interesting. I'm also assuming that at this point, or I'm hoping that at the very least, like Samantha or Vicky, if they had a question, they would ask at this point, I think, because it's clear, I totally think that they know what's going on and are participating. So I would not think any question would be dumb. It would help me, blah, blah, blah. Now I'm going to go on to the next question though. Unless there is so I think we have answers to these three. I don't think they're obvious until you do them, but once you do them, I don't think they're overly tricky, demanding rocket science problems. I think they're also harder because we're zooming, all of that. But now the next one is a little bit more tricky. And it's still based on what we did last week, or it's still trying to put together the applications of what we're trying to get over the last few weeks. So the next question, and I know it's 4:50, so okay. But again, thank you, those of you who are participating, really, really. Because you know what's really awkward about all this? I'll just say, because I don't even know if people are listening or not. You know what's weird about all this is, like, well, no, you already know what's weird about it, which is that we're all in each other's apartments. That's what's weird about it. I mean, the thing is, it's really weird that you all don't have your videos on, but I really can't blame you at all. And I can't make you, in the bottom of my heart, I can't make you, because I know how weird this is, because what do you need me in your bedroom for? Like, I don't want to be there. I don't want to be this up close and personal. So I understand why you all don't want to say things. Oh, thank you. All right. So, but that at least shows that you're hearing me. Right. No, I mean, this is weird, right? So anything you guys can do when you put things in the chat like that, anything you do to even make it clear that I'm even like being heard is very helpful, like she just did. Because I'm not going to make anybody because it is too weird. But okay, I'm going to go on to the next question. And probably that's all we'll have time for, and then we'll probably wrap up. But it's all still based on this pendulum and this motion 3. I'm sorry. Okay, this is going to be there's going to be 2 more parts to this. So this is like the 4th exercise we're doing. They're all supposed to be just exercising based on the equations we have, but I'm also trying to show that even plugging and chugging equations in physics is like not always obvious or something. But now there's going to be, I'm breaking this into 4 little parts, A, B, and there's going to be a C and a D. Just again, for anybody who's listening, there's going to be a C and a D. I'm going to put them on the next page. I'm going to put all of this on the next page again at the top. So like, because I am going to send you into the rooms again to do this. God help me. But I want to make it clear, you're going to have like 4 little things to do. And I'm going to give you the equation. I'm going to remind you of the equation that you're using for this. Or I'm going to give you the equation that you're using for this. But yeah, so I'm just going to but this, what I'm trying to say is this is still the same pendulum that we've been talking about the whole class. Like every fact we're building about this pendulum, assume it's the same one. So we still don't know its mass. I still never have told you its mass. And that means you don't need it for any of these things that we're figuring out. But we do know that it takes 20 seconds to go back and forth. And we've been figuring out all these things based on that. I'm now adding one fact and saying, let's assume one more thing about this pendulum. Assume that we know where it starts. We assume we know the angle that you let it go from, the place where instantaneous velocity is 0. Now, assume that that angle is what you might call, or might have called before this class, you might call I have to be careful. I always do this. Yeah. Is what you might call like 22 degrees, which is a fairly, I mean, that's a kind of a large angle for a pendulum like this. Like usually pendulums, we like to start at even smaller angles, like 10 or 15, but it's a reasonable angle. Like the physics will work at an angle like that. So assume you're holding this back at 22 degrees to start from, but because this is real physics, someone's here. Because this is real physics and based on the stuff we were doing last week, I'm going to say, okay, you can picture that as 22.5 degrees if you want, but I want us to get increasingly used to ultimately thinking and picturing in radians, not in degrees. So I'm telling you what that's actually called is pi over 8 radians. Now this again comes from last week, I believe, I hope, I pray. That is, remember, I'll rewrite this in a second, but remember 2 pi radian, oh yeah, we said this, 2 pi radians is 1 full cycle. So pi over 8, so pi radians is a half a cycle. Pi over 2 radians is a quarter cycle, like what you'd call 90 degrees. Like pi over 4 radians is pi over 2 radians is a quarter cycle. Pi over 4 radians is an eighth of a cycle, like 45 degrees. And we're going one step more to pi over 8. So it's like a 16th of a cycle. And you need to think of it that way to answer the questions I'm about to ask you. But assume you know that. Assume you know that. Then what I'm going to ask is, where are we actually going to find this pendulum after 1 second? Like at what position? I mean, maybe it's a little bit further. Maybe by 1 second, maybe it's going all the way across and come back. No, probably not, because its period is 20 seconds, right? So in 1 second, it'll be somewhere. What angle will it be? I want to know where it'll be in 1 second. I want to know where it'll be at 2 seconds. And then now here's what I'm going to write on the next page. So hopefully I can fit this all. Okay, I sort of lied. I just gave you 6 exercises instead of 4. This will definitely carry us to the end of the period. This looks like a lot, but it is. I'm actually asking the same kind of plug-in question like 6 times, and I'm not doing it to drill you or to bore you. I'm doing it so that you see a pattern and you see a point. So honestly, once you get A and or B, it'll be easy to get the rest. You'll be doing the same thing over and over. Now, and in fact, this is just a plug-in. I'm even going to tell you the equation that I'm picturing here, that I think we developed last time, but whether we did or not, here's the equation that, but I do want everybody to use. Sorry. Okay. Some people hate cosines. Other people have never used cosines. A lot of people hate cosines at this point in their career. I was we're part of the purpose of this class, honestly. Technically, trig is required for this class, but really a big part of this class is to get people through physics to actually understand trig by the end. We don't assume that you really love trig or really have mastered it coming in. We do assume that you've seen it. And so we're going to shift now to the trig here of this. Whether or not you feel like whether or not I explained this equation adequately last time or not, I will explain it again next time and over, like for the rest of our lives together. But I want to practice using it right now. This equation that I just wrote in orange. You're going to use this equation in orange to solve these 6 questions right here. If you already know what's going on, or if you get that, you can start right now. Like the faster we get to these, the faster we're done with class. I mean, so this is what we're doing until to get us to the end of class. We're plugging in this equation right here in orange to get answers for these 6 little moments. One thing and it does say what it means, or it does mean what it says. It says, in order to get theta at any moment, in order to get the angle of this pendulum at any moment, in order to predict where it is angularly, you're going to take the cosine of its angular frequency times time. Like you're literally going to take the time that I'm looking for, multiply by the angular frequency of this pendulum. So you're going to take the cosine of that and then multiply by its initial position here. And that will give you its position at any given moment you want. Like that's what you're going to practice right now. It's easy, it's plug in. If you get it, it's not. If you don't, but one thing is you certainly have to use a calculator for this, or you have to know your sines and cosines somewhat well. If you're using a calculator at all, which you're certainly welcome to, you must. This is all about radians now. We are about radians and radians per second. So calculator. Our goal for the end of this class is to solve these 6. Certainly, if anybody at all has the skill or the gut or the whatever, if anybody feels like they've got answers to these 6 and wants to share them, if we get right answers to these 6, we're out of here. Like, I don't mean to but as a motivation, the faster we get to the end of this, the faster we're out of here. I will explain it all though, and I won't intentionally drag it out, of course. I'll explain it all if necessary, and I'll take a half hour to do it if left to my devices. But if anybody else can get there faster, all the power to you. We won't do anything else besides this, I guess is what I'm trying to say. So what I'm actually going to do, I'm going to put you all in a breakout room together, and I will leave that room until, except when I'm there. Oh, wait, hello, oh, wait, oh. Oh, no, right, okay, wait, sorry. Right, so the starting point for this pendulum, good question. The starting point is this thing right here, is pi over 8 radians. In other words, in English, what I'm saying, the starting point is that we pull it back to about 22.5 degrees. That it is 22.5 degrees is a starting point here. Only I'm saying you can picture 22.5 degrees, but in order to do calculations or use this equation or whatever, you're going to have to know that number expressed in radians is pi over 8 radians. So the starting point for this pendulum, is this number right here that I'm circling, and that is what I mean by this number right here. So I don't know if so my answer is that the starting point for this pendulum is pi over 8 radians, which, and by the way, let me say to everybody, cool, okay. To everybody, here's the thing too, really, the physics is we're talking about oscillators. We're talking about masses on springs, pendulums, and again, by the way, why do I care so much about oscillators? And like, what could be more boring? Truthfully, oscillators, first of all, they are clocks. Like what we're really analyzing here is the physics of all clocks in the whole world, but also little oscillators, when you put them together, make waves, and waves are how we send information through the universe, whether it's electric fields or sound waves or magnetic fields or light, and all of which is what the course is really about, is sending information through the universe without matter. we're trying to figure out how waves exist in the universe that are not comprised of matter. And they're built from these oscillators. So again, this is just to everybody. We're worrying about oscillators right now. And with all oscillators, it's true that the thing that's easier to picture or measure or see or think about is like period and frequency. Period and regular frequency is what you can see with your eye and measure. But what we can do math with, what the math works on, is radians and angular frequency, because the mathematical way to analyze cycles is to use the math of circles. So the hard thing for everybody is so what I'm trying to say to everybody right now is the hard thing really that gets in the way of physics is this clunky business of radians and angles and cosines. Like and so secretly what we're really doing here in this class part is trying to force everybody's clarification of, I'm saying what the real issue is, no one really likes radians when they come in. We're trying to force ourselves to get to know radians. The starting position of this pendulum is measured in radians. It's pi over 8. I'm looking for an answer in radians to each one of my 6 little questions here. But in a way, all I'm asking you to do is plug back and forth. But yes, you need, the starting position is easiest to picture in degrees as 22.5, but you're going to have to get used to thinking of it as radians in order to do the math. I guess is what I'm saying. But all right, I'm going to shut up. I'm actually, wait, we don't even have that much time. I'm going to put you all in a breakout room that has everybody but me. So just any way you can try to get answers to these, and I am saying plug in the equation, great. And then if anybody wants to come out and send me a message like we're done or whatever, then we can be done or not. Or if you want to come out and say we give up or whatever. But I'm not going anywhere. I'm right here. I'm just doing this because I'm just trying, because I'm a desperate man in a desperate situation. So, all right. But again, these 6 exercises is our goal for today. Oh, and let me say also, I'm going to say this. Why don't we say this? Before I give any new homework or anything like that, those of you who are really, you are coming to class, you're trying, I see that you're here. These 6 exercises, like, we're going to get the answers together, but then I'm going to post a homework like link that is just this. I'm going to ask you just to write this up, not in any big elaborate way, but just pretend it was a homework thing and submit it once you see the link. When you see the next homework link, it's going to be asking you just to turn in what we've done today, essentially as your reward for being here, if you want to think of it that way. And you'll get full credit. Of course, your answers will be right because we're going to have gone over them. And maybe that's a habit we should get into. I'll just ask you, just like I send you guys the notes after every class, I'm thinking out loud right as I'm saying this. You may or may not be hearing me, but look out for any next homework link may very well not be some hard new thing. It'll just be asking you to submit a written version of what we did here so that we're all accountable to each other. And so you get this reward for having worked it through. All right, that said, I'm putting you in a breakout room. I'm putting everybody there but me. The faster you get answers, the faster we're out of here. Wait, sorry. Yeah, so please, right. So it's just all you together, just like crunch this, do whatever you can just to get these answers for these 6. Cool, cool, cool. Cool. And Carolina, you're cool? Can you hear me? Oh, cool thing, or cool. Anastasia? Carolina, can you hear me? Anastasia, can you hear me? Hello. All right. So, I don't know. Did you guys get any answers? Is there anybody who wants to say any answer at all, or any thought, or any step, or anything? I know we're going to wrap up in like, we could wrap up now. We've got 15 minutes. We could wrap up now if anybody would give me anything to work with, like a step one, or even, you know what? Even if someone in the chat just wrote out what they understand the first question to be, if you even tell me what the question is that we're working on, that would help me a lot. Any of you, like, it would indicate that you've been working on something. Any thoughts? Notice I am doing the solution as I'm talking. I mean, this is the solution, but I'm not going to give away anything quite. I mean, I'm setting it up. Any thoughts? Like, did anything happen in the room? That's a weird question. Okay. Control of the experiment. Raise your hand if you can hear me right now. Please, like, raise your electronic hand if you can hear me right now. Oh, wait. Does this mean? Oh, thank you, Samantha. Totally on the express train to heaven as she is. And now you know. Why is it always the same? Cool. Thank you. Okay. Oh, she's back. Oh, no, it's Tiffany. Okay. Thank you very much. Okay. So you can hear me. So did you guys get any? Do you want to say anything, or you just want to see? I mean, I'm doing it here, but you got to hear it. Okay. I mean, can I just ask, did you get an answer to number one? You don't have to tell me what it is, but okay, raise your hand if you got an answer to A. You're not going to share it with me, or I'm not going to demand it. We'll find out if it's right or wrong, but can you just raise your hand if you got an answer to part A? One person. Okay. Well, all right. Well, this is the solution. Get a little bit. All right, and you can put your hands down. Well, this is what I'm doing. I'm going to go to the next page. This page, I'm going to actually get answer A. We're going to get answer A here. Yeah, and then I think I'm going to have to turn it to you guys for B. Otherwise, can't live with myself. But while this is scrolling out, and I mean, I'm assuming at this point that if people really had an answer to A, then they would jump and tell me, oh, wait. Yeah, Katerina, I answered that question. Right, so about the PDF, okay, one thing is, it's totally a legitimate question whether I would send a PDF version of my today lecture, but here's the thing, I totally do every time. Yes, I will absolutely send, so I will absolutely send a PDF of these lecture notes right when we're done. I will today, and I do that every time. That is definitely part of the class, but it's a little, now I'm getting a little concerned that question, like that question was asked.
Yes, thank you, Professor. So each lecture will be uploaded video and PDF, right?
Yes, yeah, exactly.
Okay, thank you, Professor.
Oh, no problem. Okay, cool. Okay, so, and for this one, so for exercise A, to get to the point, I'm saying that the answer to A is 0.373 radians. All this is approximation. We're chopping off digits somewhere, but the answer to A is approximately 0.373 radians. Now that's a little bit hard to relate to if you can't relate to what a radian is yet, but to put it in perspective, remember this pendulum started at an angular position of pi over 8. That's a little hard to picture again, but that's about 22.5 degrees. But if you just do the conversion, like pi over 8, pi is a number. So if I just divide that number by 8, I get about 0.393. Like the original position of this pendulum was about 0.393 radians from the center. What we're now concluding here, if I just plug and chug this equation, is that at t equals 1, it moved in a teeny bit, like it moved into 0.373 radians. That makes sense to me, that like this answer for number 1 to me makes sense because it's very super close to the answer 0.393, but just close to it. It's a little bit less, like the pendulum has fallen a little bit. Okay, this pendulum within 1 second has fallen a very tiny bit from like 0.393 and to 0.373, like on its way falling to zero. It makes sense to me that it's fallen a tiny bit in 1 second because remember the period of this pendulum. Yes, I can. Good question. But remember the period of this pendulum is 20 seconds. It takes 20 seconds to go there and back. So in 1 second, it hasn't gone very far at all. But yes, wait, I'm looking at the chat. I see. Can I show the? Yeah. So how I got it was, and thank you. I'm so glad you asked. Like again, that makes me feel like you're in the class. How I got it is right here. And if you take your time to copy it, as long as it's doing something for you. I don't need to skip around. This is how I got it right here. I can even. I'm showing this to everybody. I can go back one more. This is how I started. This is the whole solution. It's 2 pages. I'll start here. I don't know exactly what you, but it's just writing the givens again. Here are the givens. But the main thing I'm using here, the thing we're all practicing is this equation that I just circled in yellow. It's all about plugging into this equation now. And I hate to say plugging, but this equation says that you need angular frequency to plug in. And that's why we were practicing getting that before. So first I solved for the angular frequency here at the bottom. I got, which we had already gotten, by the way. We had already gotten before, or like Vicky or someone had already gotten that angular frequency. We could do it different ways, but we've got it, 0.314 radians per second. So then again, tell me if you want me to go back, but then on the second page, I have that, and I'm plugging it in to the equation using 1 second for t. So you got 0.314 radians per second times 1 second. The seconds cancel, and we take the cosine of 0.314 radians. And by the way, and again, thank you for asking. Can you show that again? And thank you, Ekaterina, for asking about the notes. At this point right here. Once anybody ever asks you to take the cosine or the sine of something, unless it's like a very, very, one of the very special angles, if someone asks anybody to take a cosine or a sine, look, I feel like I understand cosines. I feel like generally at the beginning of Physics 102, a lot of people don't understand cosines, and there is no shame in that. I hope that by the end of Physics 102, people do understand cosines, but here's the thing. Even I do feel that I do understand them, and if anybody ever asks me the cosine of anything, I always plug into a calculator. Like I have a feel for them, but it has to be done on the calculator. Everybody plugs into the calculator, so the moment you press cosine in your calculator, you're not cheating or anything like that. Everybody has to, but you do have to make sure the calculator is in radian mode. Otherwise, the whole thing blows up. Like this is one of those times that actually matters. But so I did. So I took the cosine of 0.314 times 1, plugged it in, and I got my answer. I don't know. Oh, thank you. So thank you for asking now, because we are starting to run out of time. We got like 7 minutes. I was hoping I'm going to just fly through the next few. I'm going to do them fast. I'm just going to write them right in front of everybody, and I'll try not to talk. There's like 5 more to do. In a way, they're all just plug and chug the same way. So I should be able to do them fast. But what I want you to see as I'm writing down the answers is there is a pattern to the answers. There is something that makes sense that's going on, is why I asked for all these special points. So bear with me. So I'm going to write them, and then if we run out of time, we're just done. But please write these down with me, or please understand they're not random exercises. It's meant to show a pattern. So that was at t equals 1. Okay, this is what I said. Now, again, same equation. Okay, and again, this is all the same pendulum. We're just watching this pendulum in operation. It's this pendulum described by this angular frequency and this initial position. So now this time, and this time I'm leaving out the units just so because they're the same every time. So. Now I'm going to have to turn the page. I'm going to pause for a second. Time is running out. So again, if you can ask me if you want me to go back a page, any of you can. But again, this will all be posted and blah, blah, blah. But this is the moment where you have to go, you're going to punch into your calculator and you have to be in radian mode. Otherwise it will be wrong. Right. Well, I'll just Okay, once you plug into your calculator, you're going to get an answer approximate, like I'm rounding, I'm chopping off digits, but approximately 0.318 radians. That's the answer to B. Notice, I'm just going to flip back for a second. Notice we started at 0.393, fell down to 0.373. Now we're at 2 seconds, we're falling down to 0.318. We're still falling. We seem to be falling faster and faster because we are, because we're accelerating because of gravity, but we are falling closer and closer to the 0 line, but that was only at t equals 2 seconds. So we're still way not there, right? Remember, this whole thing is supposed to take 20 seconds to go there and back. So now we're at the second, swooping in towards 0, right? And we've got like 4 minutes left of class. So then the next question I asked, but I'm just plugging in and plugging in to see this pattern. The next one I asked, I forget, was, I think I asked at t equals 17 probably. Wait, sorry. I mean at 18. Oh, 510. Okay, sorry. Oh, I see what, yeah, sorry. So now I'm going to do it at t equals 5. I'm just going to plug in the same thing again. Again, if you didn't do it before, but now you're seeing the point, you might want to just try to race and do it while I'm doing it and beat me. But we're saying this again. Oh. Okay, now again, I'm aware that the class is just about over. Just notice what's happening here. I'm now asking at t equals 5. We're just plugging it again, this random cosine thing that I'm sure like all seems obscure and irrelevant. But then look how nicely it's starting to work out. We plug in for t equals 5 and we get something very close to 0. Not because I made a mistake, like it's like 0.00000 on my calculator. So I round it to 0. That's not a mistake and that's not outrageous because this whole thing we said it's supposed to take 20 seconds to go there and back. So 20 seconds. So in effect, by asking what's going on at t equals 5, I'm asking what's going on at a fourth of its period, right? Well, if it's taking 20 seconds to go there and back, then it's probably taking 10 seconds to go there. So it probably took 5 seconds to go halfway there and halfway there. It's at the bottom. It's at angle 0. Like this does make sense when you think about it. And so I'm just going to fly through the other. I'm going to try to shut up and just fly. I know we got like 2 minutes. I'm going to, well, basically we've got 1 minute. In 1 minute, if you have to go, just go. Other than that, I'm just going to write down the rest of the answers. And if you want to stay and just see the answers, that'd be great. I'm going to try not to say much about them. But if you have to go, go. And then this will all be posted. But I'm just going to write out these final answers or this final solution for this whole thing just for completeness. So for anybody who can hang out and watch and see it or copy it, great, great, great. If you can't, you can't. But and you could totally ask questions. But I'm just going to complete this sort of quietly. and then say goodnight. So if you have to go now, go. No harm, no foul, no hard feelings. All you're missing is like the rest of these answers. But you can maybe even predict like the next question I believe I asked. The next question I asked was, what's it doing at 10 seconds? Look, I'm about to do it out. I'm about to do out the math. But if this is making any sense, we should get an answer of negative pi over 8, right? We should get the same, we should get that it's all the way on the other side. We should literally get, we should get pi over 8 on the other side, which is to say 7/8 pi, if you know what I mean. Like, you'll see what I mean. But we should get, yeah, 1/8 of pi from the other side, which means pi. Anyway, we're going to get 7/8 pi if what we're doing makes sense. And again, if you have to go, just please go. And I won't even know. I totally get it. All right, 10 times 0.314 is 3.14. So now we have the cosine of pi. What's the cosine of pi? The cosine of pi is -1. So that's just what I was saying before. That's nice. And then that's the answer. And then E. I just want to make sure this is the question I asked.
Can you show that answer?
Oh, yes. I'm sorry. I'm sorry. Yes, absolutely. Sorry. I'm just checking back what I want to make sure the next question was what I think it was. But yes, I can show that again. Thank you for. 19. Okay. Yes. Show the yes. Yes. You mean this, right?
Yeah, it's like the bottom keeps on getting cut off for me.
Oh, sorry. Yeah. So and by the way, yes, totally. That the bottom is supposed to be saying theta equals negative pi over 8. So pi over 8 on the other side of the pendulum, in effect. Does that make sense?
I wrote it down now. I'm good.
Oh, you're good. Okay, thank you. But thank you again for me. You are good in more ways than one. Okay, so that's the answer to that one. And I know I'm keeping you late too. That's that. So then E. Okay, this looked like 19. Who could do this in their head? But if it's the same thing again. And so now notice this again, I'm just plugging in over and over into this obscure looking weird cosine thing, but look what's happening to the numbers. I know we're just about done again, but look, not coincidentally, at 19 seconds, I get the same answer as I do at t equals 1 second, that 0.373 answer. Like, and that makes sense because what we're saying is this whole thing takes 20 seconds to cycle there and back. So 1 second in, it's at the same place as it is 1 second from the end of that cycle. This is what cycles mean. And what we're really trying to show here, and I'm just about done, I really probably keep saying, we're really just trying to show how the cosine function does capture that behavior. The cosine function does this thing of going up and down appropriately. And then, so then our final answer, when I finally asked, if I had then asked what's the answer at 20, the answer would be pi over 8. But instead I asked, to cut to the chase, this is the very last question, I asked at t equals 2t, what is theta? Now that looks like an obnoxious, like, wait, what is that? Wait, I was just getting used to this and there was numbers. What's t equals? What I mean is, remember, by capital T, we mean specifically that period of time for one cycle. Like lowercase t means any old time at all, but capital T means period of one cycle, which in this case here was 20 seconds. But if so I could plug in, so I could for this, and this is the last thing we're going to do, I could say, $2t is just a fancy way of me saying 40. So I was just being, you could just plug in 40, like 2t means 2 times 20, 40. You could just plug in 40, but then you could ask, well, why do you have to be obnoxious, Yaverbaum? Like, why do you have to write it that way? Why don't you just freaking write it as 40? But the reason I did is because I just want to like capture, like, once you get what's going on, you don't even have to plug in anymore. At 2t at 40, like that would be going there, back, there, back. It should be again at that same place of pi over 8. It should be where it began because it's exactly 2 periods later. If it were 3 periods later, we should get pi over 8 again. Like if you literally plug in, you will see that that's what we get. But I've kept you 10 minutes late. You guys, you really, especially those of you like Samantha, those of you who are saying anything, I really appreciate it. Those of you who are actually following everything and writing it down, even if you're not saying anything, then I totally appreciate that. And I get that too. And it will become more and more clear that you're doing that. I know this is hard. I know this sucks. There won't be anything hard to do between this week and next, but I might ask you to submit this work that you did here. I will post the lecture. I will post the notes. I will leave you now. You are all going, ye shall inherit the earth. I mean, are we good? Can I go? I mean, are we all good? Shall we go? Or if I get 1 thumbs up or something, I'm good. Yes, have a day. Thank you. You have a nice day too. You are beautiful people. Good night.